Hello, everybody. Welcome to the lecture for April 1st, April Fool's Day. Sorry this is going up a little bit late. I had several meetings with small groups today, so I'm recording this a little bit late, but it is going up, and I hope you have some time tomorrow to look it over. So without further ado, we can go into the lecture. Just one more remark. Please, if you haven't already, form a group or let me know that you plan to work on your project alone, and schedule a meeting with me to discuss the project and what the expectations are. I'm going over those expectations with each group on their own and outlining a summary of each of the projects if a group has a specific interest in one of them. Okay, so last time we left off looking at these permutation groups. So permutation groups are groups of functions, right? So these S3 is a set of functions from the set 1, 2, 3 to itself. And I not only want them to be functions, but I want them to be bijections. And the reason I want them to be bijections is because if you remember, one of our group axioms is that every element of my group is invertible. So I need bijections are exactly the functions that are invertible. So I need all of these my group elements to be bijections. And there are exactly 6 bijections from 1, 2, 3 to 1, 2, 3. 1, 2, 3, 4, 5, 6. And we went over these last time. So for instance, the identity function just takes 1, 2, 3 and sends it back to itself. You have these 3 which swap the roles of 2 numbers. So 2 and 3 here get swapped and 1 remains the same. 1 and 3 get swapped and 2 remains the same. And then 1 and 2 get swapped and 3 remains the same. And then you have these here which sort of go around in a circle. 1 goes to 2, 2 goes to 3, 3 goes to 1. So it's like I'm rotating by my 1, 2, 3. This goes to this goes to this goes to this. It's a circle. And this is sort of the reverse circle. 1 goes to 3, 3 goes to 2, 2 goes to 1. So it's the circle in the opposite order. And these are the only permutations of the set 1, 2, 3. Okay, so what we're going to do today is we're going to look more closely at this permutation group, and we're going to identify certain sets associated to one of these permutations. Remember, an element of the group is a function. So if you give me a function, I want to sort of associate some data to it. So for today's lecture and Friday's lecture, the main topic will be how we notate and talk about these permutations. And to introduce one of these notations, we need to get to a theorem, and we need some structure for the permutations. So the way in which we notate the permutation will exactly be a reflection of the theorem that we prove to get there. So what's our notation? This is sort of the most basic notation. That's not. This one is extremely cumbersome. This one's slightly better. What I do is I list the inputs of my function at the top row. And at the second row, at the bottom row, I list the output. So 1 goes to this, 2 goes to this, 3 goes to this, and goes to this. So if I look at the functions I have here, and I wanted to write them in this new notation, they would look like this. So for instance, A is the function that says 1 to 1, 1 to 1, 2 to 3, 2 to 3, and 3 to 2, 3 to 2. 3 to 2. Right? B is the function that sends 1 to 3, 2 to 2, and 3 to 1. And so on and so forth. It's just a way to write it down without having to draw the messy arrows every time. So this is a very convenient way to do it. It does make it a bit harder to see how to compose functions, right? The benefit of writing them down with these arrows is that if I want to do B of A, I can write down A and then B and just look at what happens arrows. Here, if I wanted to compute B of A, well, I'd say, okay, the first thing I apply is A, so if I wanted to input 2, 2 would go to 3. And then I would say, okay, now I need to look at the input 3 for B. 3 goes to 1. So 2 would go to 1 for this composition. So I hope that this notation is clear. The main thing we're going to try to do for the rest of the lecture today and also on Friday is develop a new notation. But to do that, we need, as I said, we need to prove a theorem. So, and the first thing we'll do is prove a definition. So an element of the set that the permutations is acting on is called fixed by a permutation, right? So sigma here is a function. It's an element of my group. So sigma is a function from 1 to n to 1 to n. It's called fixed if it doesn't change under sigma. So sigma takes that number back to itself. So for instance, everything is fixed under the identity. Only 1 is fixed under A. And so on. Here, right? The fixed point set of A is just 1. If a number is not fixed, we call it moved. So the moved set of A is everything else, 2 and 3. And this is just notation. Fix of sigma is my function here, is the set of fixed points, and move of sigma is the set of moved points. So I have these two examples. D, for instance, everything moves, right? Nothing stays the same. This is this rotational picture. 1 goes to 2, 2 goes to 3, 3 goes to 1, and so on and so forth, right? Do, 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 and so on and so forth. So C and D are special types of things. In fact, everything in S3 is a specific type of permutation called a cycle. But we're not there yet. Sorry, I jumped ahead a little bit. So two permutations are disjoint if the moved set of one of them is fixed by the other one, and vice versa. So sigma moves around a bunch of things that pi fixes, and pi moves around a bunch of things that sigma fixes. So one of the main theorems that we can prove, it's not a main theorem, but it's a theorem we can prove, is that disjoint permutations commute. So it's not true that these are the only permutations that commute. You can have two permutations that are not disjoint that still commute, but once they are disjoint, then they have to commute. So let's try to write a proof of this statement. So first, let K be an element of 1 through n. Then, so what happens if I try to do sigma of pi of K? Well, pi of K has two options. So if K is an element of the fixed point set of pi, well, then pi of K is just K again. And pi of sigma of K is what? Well, I want this to be equal to sigma of K, right, if it commutes. So I need to show that this thing is still equal to sigma of K. So what do I need to show? I need to show that if K is in the fixed point set of pi, then so is sigma of K. But what do I know? I know that the move point set of sigma is contained in the fixed point set of pi, right? So things that move under sigma are fixed under pi. So I just need to show that sigma of k is also moved. Otherwise, if k is an element of the move set of sigma, if sigma of k, if k is in the fixed point set of sigma, then all these things are all just equal to k. Right, so how do I show this? Well, my assumption is that k is moved. So since k is in the move, or I should say if k is in the moved point set of sigma, then sigma of k is not equal to k. But sigma itself is a bijection. So I can apply sigma again to both sides of this equation. So since sigma is injective, sigma of k is not equal to sigma of k. Which means that sigma of k is moved, right? When I apply sigma to sigma of k, it's not the same element anymore. So this is the argument in this case. Now I need to do, that shows that these two things commute if k is in the fixed point set of pi. So now what happens if k is not in the fixed point set of pi? Well, then by definition, k is in the moved set of pi. And by assumption of disjointness, the moved set of pi is in the fixed point set of sigma. So now I can do the same thing, the same procedure, just reversing the roles of sigma and pi. So let's go through this procedure a little bit more cleanly in this case. So if they're both if k is in the fixed point set of both pi and sigma, then obviously they commute. Pi of sigma of k is equal to k, and sigma of pi of k is equal to k. So now I assume that k is fixed by sigma, but not fixed by pi. So if k is in the moved point set of pi, then pi of k is also in the moved point set of pi by an argument similar to that above. But by assumption, the moved point set of pi is contained in the fixed point set of sigma. So pi of k is fixed by sigma. So when I plug it into sigma, I just get pi of k back. But k, by assumption, was in the fixed point set of sigma, because it's in the move point set of pi. And that's exactly the claim that sigma and pi commute. So this proves the theorem. Sort of, pi is operating on one set of numbers and sigma is operating on the other set of numbers. And the things that sigma moves, pi doesn't, and the things that my pi moves, sigma doesn't. So here's an exercise. And I'll probably write it in this week's homework that I'll publish on Friday. If pi and sigma are disjoint, then the moved point set of pi sigma is the moved point set of pi together with the moved point set of sigma. Is the union of these two sets. This is not true in general. This is not true if sigma and pi do not commute. For instance, or are not disjoint. Even if they commute, it's not true. If pi is equal to sigma inverse, then they commute because their pi sigma equals sigma pi equals the identity. But the move point set of the identity is empty, whereas these move point sets are probably not empty. So this is really a theorem only about that only works for disjointness. Okay, and now we get to the crux of the matter, which is cycles. So a cycle is a specific type of permutation in which the moved point set is listed, can be listed in a certain order, right? K1 up through Kr, where sigma sends Ki to Ki plus 1, so sigma sort of moves each of these along one step at a time, and then sends the last element back to the first. So it's I march along, get to the last element of my cycle, and then get back to the beginning. And this number r is called the length of the cycle. So let's look at an example. So this is a cycle of length 3. Right? Because what do? I have the elements 1, 2, and 3. 1 goes to 2, 2 goes to 3, 3 goes to 1. This is sort of not reflective of the general cycle structure, and that's exactly because these numbers don't need to be listed in order. So let's do another example. This is also a cycle. So let's draw what happens here. So 1 and 3 are fixed. So the cycle doesn't have to move every element of my set. It just has to move, the things that are moved have to move around in a circle. And the things that are moved around here in a circle are 2, 4, and 5. The other key feature is that they don't need to be moved around in order, right? So in this case, 2 goes to 5, 5 goes to 4, and 4 goes to 2. So this is also a cycle of length 3. This one belongs to S5, but this is a cycle of length 3 because I have my fixed point set has size 2, and these 3 elements are moved around in a circle. So cycles will play a crucial role in our main structure theorem for this section. And so what I'm going to do for the rest of today's lecture is state the theorem and then give some examples of the notation that comes out of this theorem. So here's our theorem. I think it's 4.1.3. Every permutation, so every sigma in S, and yesterday I used S sub n. I'm going to now switch to the book's notation, which is S of n. Every sigma in S of n can be written uniquely as the product of disjoint cycles. So when I say product here, I mean group product. So it's the composition of disjoint cycles. So let's do an example. Let's do a permutation of 7 things. Let's have 1 go to 5 and 5 go to 1. Let's have 2 go to 6 and 6 go to 2. Let's have 3 go to 7, 7 go to 4, and 4 go to 3. All right, so this is an example of a permutation, and maybe you can see from the way that I pasted and filled in the permutation what the cycle structure is. Right, I have 1 and 5, which are permuted between themselves, so this is a cycle of length 2. I have 2 and 6, and then I have 3, 7, and 4. So this is another cycle. So this picture indicates what the action of the permutation is, right? The permutation, let's just recall one more time. S of n is the set of functions from this set to itself. 1, 2, 3, 4, 5, 6, 7, back onto itself. So 1 is going to have to go to 5. By definition, sigma of 2 is equal to 6. Sigma of 3 is equal to 7. So this is the notation we discussed at the beginning. So these pictures are another way to document what the function is doing. Sigma, the image of 1 under sigma is 5, and the image of 5 under sigma is 1. So if the function is a bijection, every bijection has this cycle structure. And this brings us to our last notation, which is cycle notation. So rather than listing all the elements here and their images down here, I just list the cycles that appear in my permutation. So 1, 5 is a cycle. I just list the elements of the cycle as they appear in the cycle. So 1 goes to 5, and then I wrap around back to 1. So implicitly, the definition here is that the last element of each cycle gets mapped back to the first one. And I use these parentheses to block off which cycles are which. So this is a cycle of length 2. This is a cycle of length 2. And this is a cycle of length 3. 3 goes to 7, 7 goes to 4, 4 goes to 3. So what is this theorem saying? This is the expression that appears in the theorem. Now the order in which these cycles appear doesn't matter, because we just proved that, well, these are disjoint cycles, so they all commute. So the order in which I list the cycles doesn't matter. So uniquely here means the product of the cycles themselves are unique, not the order in which they appear. The order in which these things are listed also doesn't matter. Here it matters slightly, but here 1 and 5, 5, 1 doesn't matter. 2, 6, 6, 2 doesn't matter. Here 3, 7, 4 is the same as 7, 4, 3, which is the same as 4, 3, 7. Because, right, so remarks. Let me explain a little bit more about what I mean here. So 3, 7, 4 is equal to 7, 4, 3. Right? Because what is this notating? This is notating a function. This function sends 3 to 7, 7 to 4, and 4 to 3. This is the exact same function that sends 7 to 4, 3 to 7, and 4 to 3. So these are not equal to what would happen if I just swapped the order of the first and second. Right? Because this sends 7 to 3 and 3 to 4. So permuting within a cycle isn't allowed unless sort of I'm just changing the start point of my cycle. Right? The reason these are the same is that this cycle is the same as this cycle, but I'm just considering 7 as my start point instead of 3. And the same here. If 1, 5 is the same as 5, 1, because I can just change the start point to 5. What are some other things that I wanted to say about cycles today? Composing them, right? So the benefit of this notation, and even previously the notation I drew with the arrows, is that it's kind of easier to see what happens with compositions. So if the cycles are disjoint, then they commute. But if they're not disjoint, then it's sometimes not clear what the composition should be. So let's say that I wanted to compose the cycles 1, 3, 2 of times 3, 4, 2. Okay, and I wanted to write this with its own cycle notation. So one way to do this is to look at where elements go, right? Let's identify the cycle that has 1 in it, right? No matter what cycle 1 belongs to, right? It has to belong to at least one cycle. Maybe it's fixed. It's going to have to go somewhere. So I think of these as functions, right? So they have to act on 1. So 1 under this permutation is fixed, right? So 1 gets sent to 1 because it's not part of this cycle. And then if I plug it into this one, it gets sent to 3. So when I do this one and then this one, 1 gets sent to 3. So now I want to finish the cycle. And so I need to see where 3 goes. Well, if I plug 3 in, 3, if I plug it into this cycle, gets sent to 4. And then 4 is fixed by this one. So 3 gets sent to 4. Now what happens if I plug 4 in? 4, I plug it into this cycle first. 4 gets sent to 2. 2 gets sent to 1. So 4 gets sent to 1. This cycle is actually wrapped up now. It's done. So now I look what happens next. What's the element that that's not listed in the cycle? Well, it's 2. Let's see where 2 goes. 2 goes to 3 under this one, and then 3 goes to 2. So this is a cycle of length 1, which is just to say it's fixed. So this is redundant. I just write 1, 3, 4. So this is an example of how you compute the composition of two cycles. Let's do one more before we wrap up for the day. So example, let's say that I wanted to write using cycle notation the product of 1, 5, 4, 3 and 2, 3, 1, 6. Okay, again, I just want to list out the cycles that appear. So 1 goes to 6. So I start with, I want to build up all of the cycles that appear in this way. So I can build them up starting from, the cycle can start from any of the base points that appear. So I want to find the cycle that contains 1. So 1 goes to 6 under this. 6 is fixed under this one. So 1 goes to 6. Now, to see what happens next in the cycle, I see what 6 does. Under this permutation, 6 goes to 2. 2 is fixed. Now I see what happens here. 2 goes to 3. 3 goes to 1. Oops. So 2 goes to 1. 2 goes to 3 under this one, and then to 1. So in this composition, if I start here and end here, 6 goes to 2. Oh. Sorry. 2 goes to 3. 3 goes... 6 goes to 2, and 2 goes to 1. I'm sorry. I was right the first time. So now I've finished one of my cycles. One of my cycles is length 3 for this composition. So I want to find the next one. So for the next one, I find the first number that's not listed here. So I have 1, 2, and 6. So the first number that's not listed is 3. So let's find the cycles that contains 3. So 3 maps to 1. And then 1 maps to 5. So 3 maps to 5 directly under this composition. All right? If I plug in 3 here, it goes to 1 and then to 5. So 3 goes directly to 5 under the composition. If I plug in 5, 5 is fixed by this permutation and sent to 4 under this one. So the image of 5 is 4 under the composition. If I plug in 4 here, 4 is fixed by this and then is sent to 3. So I have this cycle of length 3. And now I've listed all the elements, 1, 2, 3, 4, 5, 6. So the product of these two cycles has irreducible cycle or disjoint cycle structure given by 1, 6, 2 times 3, 4, 5. 3, 5, 4. Okay. So this shows that the products of the lengths can change quite drastically, right? Here I took the product of two cycles of length 4. These ones are not disjoint, so they don't necessarily commute, right? And it's interesting to compute what happens if I compute the opposite product. If I do 2, 3, 1, 6 times 1, 5, 4, 3. But here I multiply them in order, and I get, when I look at the reduced cycle structure at the end as disjoint cycles, I get 2 cycles of length 3 instead of length 4. By comparison, here I multiplied 2 cycles of length 3, and I only had 1 cycle of length 3 at the end. The other one had length only 1. This one had a fixed point afterwards. So composing cycles is tricky, but I hope that I've explained the notation fairly clearly. Please let me know if you have any questions. You can use the YouTube comments, you can email me, you can post on Canvas. Any way to communicate is fine. Just let me know if you have questions. So next time, we'll prove this theorem, theorem 4.1.3, that every cycle, no matter what, every permutation can be written uniquely as the product of disjoint cycles. So uniquely here means that the cycles that appear are unique, but the base point, right, the first element of the cycle, is not determined, right? That's sort of an artifact of the notation. And the order in which I write the cycles isn't unique either, because they all commute once they're disjoint. Okay, I hope you followed. Let me know if you have questions about the project or the lectures. And there will be a homework on Friday. See you then.